So now we got to the real interesting part. This is where data and data science and everything, mathematics, everything comes together. Real world data looks like this. And the question which we are going to ask today is, if I show you data that looks like this and says, is there a line here? What is our guess?
Yes.
Yep.
Yes. What is that line? Right? So we're going to do this exercise right now. Pretend that this is my data. We actually know which line it is because we created a line. It has a specific slope and an intercept. When we generated this data, we actually created it. So I actually know what is the slope and intercept. But now we're going to do like a puzzle. I give you this data and say, can you please find out what is the line and what is the slope and intercept of that line? I wanted to do this. I didn't get time. One way to do this is to add the sliders to this picture. If you want, you can do it as an exercise. I didn't have time to do this. And then you can just change the M and C and you can see a line, you can draw a line inside this data and move the line up and down. And when you think you have a good line, that's your answer. Yeah? Make sense?
Makes sense.
You can do it kind of manually, okay? But that would be difficult to do in general, right? So we have to ask the question, can we do this mathematically? Because the computer cannot find this. And also, there are many lines you can draw through this, right? So which one is good? Does anyone want to propose? How can I know which is a good line?
On which the maximum number of points would fall.
Okay, that's what. Well, it's interesting, right? Suppose there's a cluster of points in one place or close by, and I can get 20 points to fall on this line. But away from this cluster of 10 points, many points are away from.
I would say like rather than falling on a one same line, if
Yeah.
how many data points are close to your line, that's what it matters. So
Yeah, closeness is a good idea to
Closeness.
capture. Okay, so let me just, can we go back one step just to the previous image? I'll give one idea. So one idea is, as soon as you have a relationship, we have predictive powers. I want us to understand this, right? When you get the relationship y is equal to mx plus c, if you give me x, I can tell you y, yes? Make sense? Suppose I tell you the relationship is y is equal to 2x plus 5. Then I say x equals 1. Can you tell me the y value immediately?
Yeah.
Yeah. So as soon as I have a relationship figured out, I can make predictions. So why don't we use the prediction idea to create a notion of what is the best line? The best line is the one where my predicted value is close to the actual value. Make sense? Does it?
Yes.
Yeah. So that seems pretty cool. So scroll down now, and I'm going to show you this. Will we scroll down a bit? Yeah, a little bit more. Yeah, so you see, I created a function. I called it the cost function. Some people call it the loss function. But it's a simple function. All it does is you take each value of x. You take any line you like. Okay, choose any value of m and c. You take each value of x. You plug it into the relationship. You get a predicted value of y. You subtract the predicted value of y from the actual value of y. That gives you the distance, right? The only thing I've done extra is that good enough? Could I have just done that? Could I just have done y minus y predicted minus y? Could I have just subtracted the 2 and be done?
Could be.
I haven't got it.
Haven't got what?
I haven't got anything.
What does anything mean? You don't understand it or you don't see it or what?
No, how did you, I mean, is it a formula?
Yeah. So
Summation?
So let's understand that formula. That formula, it looks like a formula. It's not. I just created something by reasoning, right? I said, so what is that formula saying? The summation over I says you must do this for every data point. Okay. So what am I doing for each data point? You take the data point and you feed it into the relationship. You pick. So here's the algorithm. You can write it as a program, right? You pick any value of m and c. So what's your favorite value of m and c, Kiran?
1 and 3.
Okay, 1 and 3. You plug in for each data point. You take the data point x and you plug it in. You'll get a value for y. Yeah.
Yes.
If M is 1 and C is 3, can we do it in our head? If X is 1, what is the value of Y? So M is 1. So 1 times X is 1 plus 3. So 4. Y is 4. Yeah. So
Yes.
each time you take a data point, plug it into this relationship, you'll get a value of Y. We call this the predicted value of Y. Why is it predicted? Because it's my model. My line is telling me this is the value of Y. But I've given you a data set. The data set already has a value of Y in it. I subtract the two to find out how far is my prediction from the actual value. Okay, so immediate question is, and then I have to do this for every data point. That's what the summation is telling me. Repeat for every data point in your data set.
Okay.
A for loop, right? Easy to do. But now I'd ask the question, is it enough just to subtract them and add them together? What's the problem with that formula or that approach? What's an obvious problem?
So how far are you going to go? That is, what should be the value of
No,
Y?
it's not. It's a little tricky question, but okay, it's when you think about it afterwards, you'll say it's obvious. Sometimes my prediction can be higher and sometimes my prediction can be lower, yes? So when I subtract the prediction from the value of Y, I will get two signs. And then I'm going to add them. So the positive values and the negative values will cancel each other. So it's possible for me to add up a lot of values and get the answer equals 0. But actually, there are a lot of differences in my data. Do you see this?
Yep, I agree.
Does everybody see this? Say no if you don't see it.
Get it.
I'm not sure I understand it.
Okay, so let's pretend we have 3 data points.
Mm-hmm.
For each data point, I'm going to plug it into the function and calculate the Y value. Then I'm going to take the actual value and I'm going to subtract. Let's say there are only 2 data points, even easier. So now I'm going to try to find out how good my line is, right? And I drew a line. Actually, there are 2 data points. I drew a line very far away from these 2 data points. But I did it in a strange way that when I take the first data point, the difference between the predicted value and the actual value is minus 100. And for the second data point, the predicted value and actual value is plus 100. Then I added them together and I got the difference is 0. So is this a good line?
But I mean, it's only 2 points. So.
But still, is it a good line? It's not even, may not even be, it may not even be.
No, because they are like outliers, right?
Yeah. Yeah, but what I'm trying to say is the reason our formula is not detecting may not be a good line is because these 2 values are cancelling each other.
Okay.
Right? So the one way to do is to get rid of the sign. Okay, there are 2 ways to get rid of the sign. One, that means you're going to penalize both positive guys and negative guys are bad for us. Just because they cancel is not a good idea. So one way to get rid of the sign is to square the difference. Another way to get rid of the sign is this function called the mathematical function called absolute value, which in common man's terms is absolute value means just throw off the sign. Each time you subtract something, ignore whether it's positive or negative. So then plus 100 will contribute 100 and minus 100 will also contribute 100. Okay? So long discussion for why the square is in the formula. But actually at the end of the day, the answer is very simple. The square is in that expression because we don't want the signs to cancel off the differences. Make sense? Okay, so now what have I done? You should spend a little time thinking about this cost function, okay? But this cost function drives everything. This cost function says, if I draw any line, I can calculate how good or bad it is by just evaluating this. Okay? So we're going to write a little program to evaluate this. Now my goal is, I chose M and C at random, 1 and 3 or 1 and 5, or whatever I chose. I change the values of M and C and try to find the best value of M and C such that my cost is minimized. Does that make sense?
So, sorry, just interrupting here. Like, cost, what you're trying to minimize, you want to find the best M and C. That way, your as many as number of data points fall on the line or close to line.
So what I'm saying is this idea that we have visually, that points are close to my line, this we can see visually almost, we have converted into a formula. If more points are close to the line, this cost will be very low. In particular, let's ask the question, if the line passes through all the points, what will be the cost?
0.
0. So you see that if I can find a line that fits all the points, my cost will become exactly 0.
farthest
points
corner.
are away from the line, my cost will increase, right? And the more points are further away, my cost will increase. So the goal for us in this whole data science exercise is, can I find an MNC such that my cost is minimum? And now I'm going to ask you, how will you do this? Okay, and I'm going to tell one more thing. Minimizing the cost is the same as finding the best line. You can move the line around and find it. The idea is that as you move, so in fact, next time I can show you this. Graphically, I can show you, I can create a calculator cost function. Every time you move the line around, it will calculate the cost function for you. And our job is to change MNC and find the value at which the cost function is lowest. So now question is, how do I find this value of MNC? Am I going to do it by moving something around, or what am I going to do?
Maybe you have to start somewhere and keep checking again and again and again.
Yeah. So you can do this, right? So there are numerical ways to do this, but the general idea here is we can use some techniques that involve calculus. And this is why I want to do a kind of intro to mathematics for data science, right? Where we can actually find the answer, okay? Find the value of MNC. So it's actually turns out to be not very complicated. It's like 10 lines of math. It's not very hard, but I don't want to make it too math heavy today. So I'm just going to give you the outcome. Let's just understand. So mathematically, I can prove that the best value of M is given by the formula on the screen, and the best value of C is given by the formula on the screen. So let's look at this formula. The formula is actually very interesting. I've written it using mathematical notation just to show you the power of the mathematics. How I can express a very interesting idea very compactly, but now I'm going to explain it in words so we don't have to be scared of the mathematical notation. So what is to calculate M, what do we have to do? You have to take each value of X. You have to calculate the mean of X. Does everybody know what the mean of X is? How will you calculate the mean of X?
Yes.
Kiran?
Yeah.
What is it?
Add all x's, divide by the number of x's.
That's it, right? Add up all the x's and divide by the number of x's. So the mean of X is easy to calculate. From every data point, you subtract its mean. Okay? The same for the y's. For every data point y, you subtract its mean. And then you take the data point X and its corresponding y and multiply them together. That's the numerator. And then add up all. You want me to repeat, or you got it?
So where is the addition happening? Is it happening in the same?
Okay, so I could have written this. I used vector notation to write the formula, but that X minus X bar transpose Y minus Y bar is actually saying add it up. Okay, I wrote it intentionally in a mildly complicated math notation to show you that the mathematics is very powerful, right? It's very cryptic and clean when it's written. But now I'm telling in words. So I could write another line in this notebook, or you could write it in your notes. The expression in the numerator is saying, and I'll write the code for this, so then you'll see it when I write the code. For each value of X, you have to subtract the mean. For each value of Y, you have to subtract the mean. And then you have to multiply each Xi, each element, data element Xi with the corresponding Yi. And then you have to divide by, you take X and subtract the mean and the square of this. Okay? So let's look at all this in code. So this is in mathematics language. I want to create a little bit of appreciation for the mathematics for you, right? To say, look, at the end of the day, mathematics is not complicated. It's just that people have invented compact notations to summarize some understanding. So let's write a little code, okay? This code actually, so now after all this discussion, this little piece of code will actually calculate the values of MNC. Should I have given this as a homework assignment? Could you guys write this? No, Cassandra's like, no, I'm not even trying. Okay, so let's talk about this code. Okay, so this code is actually quite easy. So let's look at it. You give this code the values of X and Y. Yeah, it's an input. X and Y are two lists, right? Each list has all the data points in the same order. So there's two lists. One list is the values of X. The other list is the values of Y. In the first two lines, what do? We calculate the means. And in Python, calculating the mean is very easy. You sum up the values and divide by the length of the list. Right? So we got the mean. Now I'm going to write a for loop. And in this for loop, I'm going to calculate two values, the numerator and the denominator. And so I take each data point. I'll explain this for loop in a second. Okay, let's just look what's happening inside. For each data point Xi, I subtract the mean from it. Do you see that line which says numerator? If you read this line, I Actually, I'll ask Ashish. Ashish, what is this line trying to do? Can you tell me in words?
So what this line is trying to do is the same, like it takes the first
What?
element and minuses the mean,
Yeah,
multiplies by y element, minuses by the mean, and adds
yeah,
into value into the numerator.
that's
So
it.
numerator equal to numerator plus the new value.
Yeah, so it's accumulating this into the numerator for all the data points. Okay. What about the second line?
Second line is only doing it for same thing, but it's doing it for x value, but it's doing a square of it.
That's it, right? So it's very similar, these two expressions. And then I'm going to divide them. You see that I have written m is equal to numerator divided by denominator. Okay, so in programming, I have basically translated the mathematical formula into this little program. Make sense? I just explained the slope right now. M is the slope, okay? But let me explain the coding part of this. Why did I write the for loop like this? Can anyone tell me? Or can anyone explain how this for loop is working?
So understood the point of I, but didn't understand the point of underscore over there.
Yeah. So the point is, I could have actually used some kind of range, right? Because I know I have to loop over the x values. But to loop over the x values, what do I have to do? I have to use the length of x to calculate the range of I values that I must loop over, right? I must find out the limits of my for loop from 0 to what? So what is the answer? From 0 to what should I loop if I want to loop over a list? Suppose the length of the list is 10. What should I do from 0 to 10?
From 0 to length of list.
0 to 10 or 0 to 11 or 0 to 9?
0 to 9.
Okay, so there's confusion, right? So I decided I don't want to deal with this confusion, right? I don't want to figure out whether it's 9 or 10. I don't want to calculate anything. So Python allows me to do this. There are two functions that we can use. I could have just said for I in x. Take off that enumerate from there. I could have just said for I in x. And then Python will loop through the x values until there are no more x values left. And it will figure out whether I got to go 9 digits or 10 digits or whatever. But it doesn't tell me what is the loop index. It gives me the x values. Okay. What enumerate does is something different. Enumerate loops over the x values, but each time it goes to an x value, it gives me two values back. It gives me the index and the value. So that's why there's an I and an underscore. Okay. An underscore is a Python. Now we're learning some Python programming here. Underscore is a Python trick to say, I don't care about the value. I'm not going to use it. Instead of underscore, you could have put anything there. Right? You could have put X, you could have called it Apple, you could have called it's just a variable. Okay, so each time I go through this loop, there are two variables coming out. The first variable is the index of the X item. The second variable is the value of the X item. So to make my code look nice, I just use the index. And that's why the I is going into it. Does it make sense? I use enumerate to get hold of the index. But I used enumerate to get hold of the index because I didn't want to calculate the limits of my for loop. So I said, Python, you figure out where to stop the loop and all that stuff. I don't want to deal with it. Right? I don't want to say 9 or length minus 1 or length plus 1 or whatever. I don't want to deal with all this complexity. So my code, therefore, is clean, right? I have no calculations here. I said all the words I can say. Maybe I will pause and say, any questions? Is it clear why I did what I did?
Yep.
Cassandra?
I'm trying to follow, but yeah, well, kind of like I'm stuck on just earlier things. Like I thought, like back to M, because I was thinking the slope is the difference in Y.
Yes.
Oh, difference in
Yes.
X. So why that's different? So
No. So that is the same thing. The slope is the difference, the change in Y divided by the change in X. Okay, that is the slope. But we are not calculating. There is no line here. There's just a bunch of points.
Okay.
So can I take any 2 points at random and calculate the slope? Because the points, there's no line here. There's just a bunch of points. Once I have a line, like if I have a straight line of points, yes, you can pick any X. So that's a very good technical question. If I have a straight line of points, pick any X and Y. Pick any 2 points, sorry, X1, Y1 and X2, Y2. If you do Y2 minus Y1 divided by X2 minus X1, just subtract the Y values and the X values, you will get the slope. But because there's no line here and the points are all over the place, which point shall I take? If you take one point, you'll get a line that goes like this. If you take another point, you get a line that goes like this. So you should put some points and you should try it and see, right? You can try it programmatically or mathematically, just calculate. You cannot use the slope formula here because there are just a bunch of points and they don't lie on a line. Okay, so some little bit of thinking here. So that's why we are doing this formula. This formula actually uses all the points to find the best line that minimizes the cost function. Right, so we've solved, we've created, actually what I've done for you with this code is, you create a very big hammer. This hammer says you give me any data set. If there is a line in there, I'll find the best line.
I have a philosophical question.
Yeah.
This only works for a limited data set, right? You wouldn't be able to do it for like an infinite data set, or that doesn't make sense.
Technically, as long as you can process it in computer memory and so on, you can do it. What do you mean by infinite data set though?
Yeah, no. Okay.
Say, for example, if you take the heights and weights of all the people on the planet, that's 6 billion points. No problem, piece of cake.
Okay.
Right? So, and then there are other tricks where we can have 10 computers work together to solve the problem, etc. So, size is not an issue, or at least is an issue that can be solved. Yeah. So I'm saying we built a very powerful hammer here, and I want all of us to appreciate this hammer is, or this, we can call it the signal extractor. You give me any kind of noisy data, and if there is a line in there, I'm going to find it. All I have to do is run this code, plug the X values, Y values, run this code, it will give me the best line. Okay. And so let's run this against our data. So now it's time to do Shift Enter. Oh, sorry, I didn't talk about the intercept, but we will do. So let's see, the data was coded, the slope was, let's go back up and see when we created this data. Let's go up when we did the signal plus noise. Yeah, right here, go up, little more before the plot. One more, little bit more up. Yeah, you can see Y is equal to F. You see that inside the code, first line of code, you see that I put the slope is 2 and the intercept is 5, yeah? M is, so the function X, so where is this function defined? Let's go look at the definition of this function. Go up one more. Yeah, right there. So you see this function is just saying mx plus c. And when we coded the data, we put m is equal to 2 and c is equal to 5, I think, right? Check that again, Ashish. Below, yeah, and also below, right? Yeah, here we just plotted it, but if you go further below, no, further below, when we added the noise, yeah, we used 2 and 5, you see? So the idea is, in this case, I know what was the signal coded in there. It has a slope of 2 and an intercept of 5. Now come down below. I didn't use this knowledge anywhere. I just took the noisy data, I plugged it into this function, I minimized the cost, and I got an answer. Is my answer looking kind of reasonable? Pretty close, right? The actual slope was 2 and I figured out that it's 2 point something. The actual intercept is 5, I got 4.8. Okay, so one exercise for all of you is, remember, if you go back on top, when we created the noise, there's a scale parameter. Right on top, when I gave a scale parameter. Yeah, just above here. You see that scale parameter makes it more noisy or less noisy. So you can increase the strength of the noise. It's like a dial. It makes it more noisy. If you make the scale as 2 or 3, the points will get more and more spread out. Then you can come back and try to figure out how good is my noise signal extractor working when there's more and more noise. Okay, the data will get more and more fuzzy, and you can play with this and get some ideas. Okay.